Hi everybody, welcome to the mechanics lecture series, and I would like to welcome Dr. Prashant Saxena. He's a lecturer at the James Watt School of Engineering in University of Glasgow, and he'll be talking today about stability analysis on highly deformable electrostatic and magnetoelastic structures. Uh, Dr. Prashant Saxena has been here in the University of Glasgow since 2018. His research interests are in the mechanics of soft materials with a focus on large deformation resulting in instabilities. His recent research has been on the electromechanical and magneto-mechanical coupling phenomena and on the mechanics of slender structures such as rods, shells, and membranes. Previously, he also worked as assistant professor at the Indian Institute of Technology, Hyderabad, and as a postdoc at the University of Lausanne, Switzerland, and University of Erlangen, Nuremberg in Germany. He has a PhD in applied mathematics from the University of Glasgow and a BTech, MTech dual degree in mechanical engineering from IIT Kanpur. Thank you very much, Dr. Prashant, for joining us today. And I mean, it must be pretty early for you at 8 o'clock, and but then on a Saturday and a weekend. So, thank you for making the time, and I'm sure all of us would really enjoy the lecture, and we are looking forward to it. The stage is yours.
Thanks a lot, Ajay, for this nice introduction. And thanks to everyone for coming. Let me see. I hope my screen is visible.
Yeah, we're able to.
Yeah, okay, that's great. Okay, so I don't have the conventional slides. I have this OneNote so that I can write and talk along as we move forward. But I'll like you to interrupt me and ask questions as we go along if you have any questions, rather than waiting till the end, because that's much better. I like this interactive kind of environment. So we work at this mechanics of soft solids group at the University of Glasgow, and I'm going to talk about one of the aspects of our research, which is on electroelastic and magnetoelastic materials or solids structures. And in particular, I'll be focusing on stability. And the thing is that whenever you have soft solids, by definition, they can deform a lot. By a moderate amount of force, they can deform quite a bit. And whenever you have large deformations, whether they are compressive or extensile, you tend to have some instabilities, either material instabilities or structural instabilities, or a combination of them. And traditionally, in engineering design, let's say from 30, 40, 50 years ago, when people used to primarily work with steel and wood and those conventional materials, instabilities were considered to be a bad thing because they would typically lead to failure. So if you have, let's say, an old style bridge standing in your city, wherever you are, and if the pillar of that bridge sort of tends to buckle, it will definitely fall. So that leads to failure. But in soft solids, which are primarily used in soft robotics or energy harvesters and other miniature devices, instabilities are generally a mechanism for some physical feature. Even in several biological soft tissues, instabilities are a feature that leads to some biological function. So that's why we study instabilities, not just to avoid them, but actually to harness them and to use them for an engineering design. So the outline of my talk is going to be very simple. I'll just talk a little bit about soft solids, that why do we actually study soft solids. I have already done so a little bit. But then I'll just focus on two main things. One is using variational formulation to set up a problem, and so this is like more of a very mathematical technique, but this is the foundation for doing a lot of analysis with not just stability, but with also let's say computational methods. So people who are familiar with finite element method might have heard about variational calculus. So this will be somewhat similar to that. This helps us to get the equations that we want to solve for our problems, get the appropriate equations, because sometimes we don't correctly know what are the equations that we want to solve. And then secondly, we'll just see some examples of instabilities which are there in thin structures. I'll primarily focus on thin electroelastic or magnetoelastic structures and how do we compute them. Okay, so uh, just like a small thing from pop culture, uh, some years ago, let's say a couple of decades ago, this was the vision of the people, that how the machines would look like in the future. I mean, for those of you who are not familiar with this, these are just some images taken from some popular movies: Star Wars, Terminator, Wall-E. And the common theme here you'd see is a lot of metal. And that's because that was the cutting edge material, let's say 30 or 40 years ago. And people assume that, okay, as we move forward in the future, everything will be more and more metal, and rigid materials, and rigid links and so on. But that's not exactly the most sophisticated machine one can build. The really sophisticated machines that exist everywhere around us are in biology, are in nature. So if you look at these two things, these are just two examples. But if you know a little bit about octopus over here, octopus is an amazing creature. So it can deform. It has these tentacles which can deform very, very flexibly. But not only that, it can compress its entire body into a very, very small amount of space. It can pass through very narrow spaces. Uh, on top of that, it has a skin which can change its color as well as its texture. And the way it does is quite interesting. So on the skin of the octopus, you have, if I just zoom into that, let's say this is the skin of the octopus, you have these small pores, and these are typically micron sized. And each of these pores has certain pigments in them. And the way octopus changes its color is that it sort of just tends to expand one of those pores, and the others don't expand so much. So let's say if this was red color, and if the red color expands quite a bit, eventually what you will see is the skin changing to more towards a red red color, or maybe this could be another expansion of green color, and so on. So essentially, the way let's say the primary way with which these things work is by mechanical deformation of certain microstructures within their skin that leads to a more macroscopic change at the bigger level. Uh, and these soft machines are just amazing, and we don't really understand them very much, let alone model them. So I think that is one of the holy grails in this area in soft materials, that um, take not sort of understand the existing phenomena in nature, but also how do we use them and develop them further as engineers to develop amazing next generation futuristic technologies. The another amazing thing in your own body is this heart here. I mean, it expands and contracts. Not only that, it has these sort of mm, tissues that are let's say in some ways electromechanical. So heart tissues can be actuated by the application of an electric field. So they have these smooth muscle cells, uh, and they have this. In addition to having this electroelastic coupling, they have a lot of coupling with the fluid, that is the blood that goes through the heart. We have these. I'm not sure if it is visible here, but we have these small flaps here that open and close these chambers, uh, which have a very dynamic response to the rhythm of the heart. So in short, I mean, the main message that I want to deliver here is that the really futuristic or really complex machinery that is available around us is through the nature, uh, and all of them have soft materials, soft parts, or let's say majority of them have soft materials, soft parts. And if we can take inspiration from them and use them to develop our next generation engineering technologies, that would be something. The another important feature uh, that is related to biology comes from biomedical research. Uh, and mm, if you want to develop technologies that can interact with human beings, so for example, people are aware of smart watches, right? Similarly, there are certain smart patches that you nowadays get with some RFID QR code. But there's a lot of scope in developing biomedical implants for human beings, or let's say for animals, to develop to treat certain disorders, but also to enhance the functionality of humans or animals. And if you want to have those biomedical implants, those biomedical implants need to interact with primarily soft tissue that exists in our body. So therefore, the stiffness of those biomedical implants need to be somewhat similar to the stiffness of the tissue that we have. Let's say the tissue on the skin, or tissue in your or the or in your organs like heart and stomach and so on. So we need to understand soft solids much more better. How do they deform under various kinds of loading, and how to exploit their large deformation characteristics into developing more engineering related technologies. So here is an image that I've taken from a recent review paper, where people have sort of reviewed the different types of soft devices available these days, and what can be done later on. I'm not going to dwell on each of these things carefully, but you can see, I mean, you have these soft robotic grippers, you have components of artificial skin, you have virtual reality glove, you have smart gloves, you have you have these skin patches for measurement of your body vitals. You have all these things which are made up of soft materials that interact with humans in some or the other way. And the key primary thing here is the primary material is a soft material, and they all undergo large deformation. So assume if you have a skin patch on your somewhere on your face, and you are talking like this or you're smiling, you have very large amount of strains that come in because of even just smiling or just speaking, and that skin patch has to undergo those kind of strains just to exist on your face. So therefore we need to uh, be we need to understand and soft materials a lot better. Okay, uh, so what I'm going to do is just talk about a particular type of soft material that we have been looking at since last few years. So on the left we have this magneto-rheological elastomer, and on the right we have this dielectric elastomer. So just let's just talk about this magneto-elastomers first. So these are not very new now. I mean, I think at least people have. So this is one of the earliest paper, which is almost 25 years old now, where what they did was they just dispersed a lot of iron particles in a rubber matrix, and these particles, as you can see, the dimension here is 70 microns. So each of these particles is sort of 2 to 3 to 5 microns in diameter. Some of these bigger ones are maybe maybe 7 or 8 microns. But essentially, they are all in micron scale diameter. And if we now have a centimeter scale sample made up from this material, you really can't uh, distinguish iron particles separately. It's like a smooth continuum. And when you apply a magnetic field on, let's say, an external magnetic field, if you apply an external magnetic field on this sample, each of these iron particles will magnetize, and once they magnetize, they will be attracted towards or away the magnetic field depending on how they interact. And on a macroscopic scale, you will see a deformation of the sample that you have. And because we have the matrix, this black color area, which is rubber or elastomer matrix, nowadays people are even using even softer matrix from hydrogels. You can undergo really large deformation of the sample because the underlying matrix is quite soft. And to understand the behavior, and these magnetorheological elastomers have been quite popular recently. I'll show you in the next slide some examples where they've been used. But to fully understand the devices that you can make from them, you need to understand the physics of magneto-mechanical coupling. Similarly, on the other hand, we have these dielectric elastomers. So these elastomers they have a very simple principle which works like a capacitor. So the dielectric elastomer is inside the sandwich, and on the top and the bottom surface you can paint some conductive grease. So you make some compliant electrodes which can deform. And if you now apply a potential difference, because of electrostatic interaction, the capacitor will apply, the two plates of the capacitor will apply forces on each other and they'll compress. So that's what happens in the actuation phase. And then if you release this potential difference is over here. If you release this potential difference, you'll come back to this original configuration. And the reason we need an elastic dielectric is that you need to have a dielectric which has kind of a sweet spot of certain material properties. So you need to have a dielectric constant which sort of gives you a good enough electric field inside the capacitor, but at the same time you need a stiffness such that it just does not collapse onto each other. The two plates just if the two plates, if the middle material is not stiff enough, the two plates will just attract and collapse onto each other, and then there will be a short circuit. So you don't want short circuit happening. So that is, so therefore there are certain materials which can sort of have the sweet spot of these properties, which is, let's say, call it the shear modulus and the uh, dielectric constant epsilon. And then we can again make a lot of interesting devices with these materials. So let me just show some of these. So there are two examples. There's a lot on this slide, so let me just see here. So on the top, we have a pump that is made up of dielectric elastomer. So dielectric elastomer is, you can see it's on the top here. This sort of dome-shaped structure, which in reality the pump looks like this. This is taken from a paper by these guys, and the way it works is that there's an inlet of the fluid here, there's an outlet of the fluid here. So you can bring in the fluid, and then you can actuate the dielectric membrane. And once you actuate the dielectric membrane, it sort of can compress and just release the fluid. So you can have a combination of incoming pressure, actuation of the dielectric membrane. So to explain it further, there's an initial state where you just are allowing the fluid to come in, and as you allow the fluid to come in, the top dome, as you allow the fluid to come in, this top dome that is over there, it's going to expand because of the fluid pressure, and then you can even further apply potential difference to expand it even further. And once you remove the potential difference, the dielectric elastomer will not have that much of strain in plane, so it will tend to compress, come back, and then it will sort of release the fluid outwards. So that's just one mechanism of using these dielectric elastomer soft pumps. People have used the same principle in using tidal energy to generate to generate electricity, right, for energy conversion. Similarly, there's another example here by these guys. This is a group in Germany doing a very, very nice amount of work in soft robots from magnetoelastomers. So just to say, I mean, these are, if you look at this image over here, for example, these are lots of snapshots combined together. So these are multiple images combined on top of each other. So there is this, you have this elastomer, which is basically just like a strip of material. That's just a strip of material, and we apply magnetic field externally, and this small robot can actually roll. It can roll in this direction and move forward. It can even swim inside the water. So the way all these mechanisms happen is that if I just look at this elastomer, you can make it deform in various shapes. You can have various shapes like this in which it deforms, and by application of a combination of magnetic field, you can make this robot to move in a certain direction by being deformed in a particular position. Uh, so, uh, so, so so this is like some of the uh, some of the reasons why we study large deformation of electroelastic and magnetoelastic materials. So with this introduction in mind, I'll just try to move forward a little bit and start with looking at variational formulations. And variational formulations help us to derive the necessary equations that we need to solve the problem, any problem that we have. So I can see in the list of participants, I mean, there are a lot of students here. So I'll maybe spend a few minutes trying to just explain what they are, and then actually do this. So essentially, what variation formulations are is that you take any system of interest and you apply the principle of minimum potential energy in the case of a let's say static system. And what you say is that any system will tend to achieve a configuration which minimizes its energy. And we use that principle to find out the configuration of the system. So if you were, let's say, just in one dimension, a very simple example is if you have a function, let's say f of x, where f is just a function that goes from real to real. If you had a function f of x and you wanted to find out the values of x where f is minimum, the simple thing that you would do is you will say put f prime of x equal to 0. That will give you a value of x, which where f of x sort of changes direction, or let's say the slope is 0, right? And then but then you say that's not sufficient. I want to also check this higher derivatives. We want to check if f double prime at x naught is greater than 0 or not, right? Unless the second condition is satisfied, you don't know whether that's a maximum or a minimum, right? If the second condition is satisfied, then it's a minimum, right? But if that, let's say that does not happen, if that is also 0, then you'll go and check the third derivative. If that is also 0, then you'll go and check the fourth derivative, right? And so on. You'll keep moving forward. So essentially, you want the first derivative to be 0, but then you want to check the higher derivatives to ensure that the 0 of the first derivative corresponds to a minima, right? It can also correspond to a maxima. Or when you have higher dimension, it can correspond to a saddle point and other things. So the same things happen in the case of in our case, but now in our case, we have this function, let's call it the energy function. And now this energy function depends on another function, right? So this is something that we call it the functional. So it's a function that depends on another function. So now in the case, instead of this first derivative that you had in the simple case, you'll take this first variation of this function, and you'll take the second variation of this function, and so on. You can, and higher variations. And the problem here is, I think if it's not immediately clear, is that here you had this function that had a domain in real along the real line and the range along the real line. But here this function E does not have that. This has a domain which is some vector space, and it has a range that is a real line, right? And this vector space V that I have just written here, don't be alarmed by the word vector space. This is just a way of saying that this is a place where all the functions live. But the main idea is that this, in the case of the simple function, this real line is just one dimensional. But in the case of a function space, this is infinite dimensional, because a function can have so many different forms. Like if you just take a function on a real line, you can have x squared, x cubed. You can have polynomial function, but then you can also have sinusoidal functions. You can have other trigonometric functions, right? And so therefore the kind of functions that you can have are infinitely many. So therefore this is an infinitely dimensional space, and therefore these the simple calculus that we are used to of differentiating a function does not work anymore. There's a slightly more advanced calculus that we need to use, which is what we call as the variational calculus. So here the first derivative corresponds to the first variation, second derivative corresponds to the second variation. So essentially what you will be looking at is putting the first variation to 0, checking the second variation is positive. So that's what ensures stability. But in practice, what we normally do is we try to find out the conditions where second variation goes from positive to being 0, because that is the case where the current deformation is no longer a minimum. There's something else that will provide you a minimum, right? So that is what we call as the bifurcation point. So if these please feel free to stop me and ask any question. I don't see, I can see a chat immediately, but yeah. Okay, if you have any question, please feel free to stop me, and then we can elaborate on that further. Okay, so this is the basic criteria that we have, and that's what we do in our case of electroelasticity and magnetoelasticity. So what we do is we choose appropriate variables. So now energy depends on the displacement of the object, but it also depends on some variable that sort of defines the electric field, or the maybe some variable that defines the magnetic field. So you have to choose appropriate variables depending on the problem that you have, depending on the boundary conditions that we have. And then essentially we have to find a way to write the total energy, and then we minimize that energy to find the equilibrium. And this is all that lies behind the concept of variational formulation. So here we have, let's say, a system where this is a reference configuration of the system, and it under certain loading condition it deforms. And a very important thing here that comes up is that because you are dealing with magnetic field and electric field, they are not just within the system, within this body, but they are also outside. So you have to deal with certain free space, because these fields can exist outside the body in the free space as well. And so those of you who are probably used to elasticity would not normally consider free space, but in this case you need to consider free space as well. So I'll give you one example of a formulation. There are multiple formulations possible for a problem. So one example is this energy functional that I've written here, that depends on the, so small x here is the deformation of the body, and this capital A, this blackboard A, corresponds to the electric vector potential. So this is electric vector potential that depends on the electric displacement through this condition that D is curl of A. And if we have a body, just that what we said, there's a body and there's a free space outside the body. This is B0, this is V0. So we can write the energy based on, first of all, the energy that is stored inside the body, omega, energy per unit volume in this case. Then the energy because of the electric field that exists outside the body in the free space, so inside this area. Then the boundary condition at the free space boundary. So this is the boundary of the free space. So imagine you're doing an experiment where you place a sample of an electroelastic material inside your machine where you're deforming the sample, and then you're applying some electric field from somewhere far away. So this is the third term that sort of corresponds to that boundary condition at the free space boundary. And these are just body force and traction force at the boundary of the body. So the way you would minimize this is by
Can I ask a question if it's,
yeah, sure.
I don't know if you're going to, so are these stresses here the unsymmetric because there's some magnetic field, right? Is this internal magnetic field or
Okay, that's a great idea. Good question, actually. I'll explain that just in the next slide.
sure, yeah.
The question is about the stresses, right? I'll just explain
Right,
that.
yeah.
Okay. So before we go to that, let me just finish this one. So if you want to minimize this energy, you'd write the Taylor expansion, some sort of a Taylor expansion. So you'll say, let's say x goes to x plus delta x, and a goes to a plus delta a, and then you would in each of these systems, for example, here f is actually gradient of small x, this d is curl of a, and similarly you have these everywhere. So you would expand each of these terms. You will have a first order approximation, second order approximation, third order approximation coming from Taylor expansion, and I think a lot of engineers tend to stop at the first order approximation, but here you need to also worry about second and third order approximations because you want to also look at higher variations. So let's say you do that carefully, and then you will essentially arrive at, and if you substitute delta E equal to 0, you arrive at a set of equations that are here. And that sort of partly answers the question as well. So the first equation here is just the equation that we are probably used to, divergence of stress. So here P is the first Euler-Kirchhoff stress, divergence of stress plus body force equals 0. But then you also get another equation which is probably not very common, which is divergence of P equal to 0 in V0 prime. So if you remember, this was our body and this was the free space, and this region outside of the body in the free space was V0 prime. So we also have this stress, which you called as a Maxwell stress, that comes in the free space in V0 prime. And you can see the definitions here. So P is simply derivative of energy inside the body, which is what we have in elasticity. But outside, there is it is equal to some Maxwell stress, which is non-symmetric. So this comprises of a lot of terms from electric and electric fields, electric field and electric displacement. So I've not yet written down the complete expression of Maxwell stress here just to save some space, but it is basically stress because of this electric fields. Then you have these boundary traction on the boundary of the body, but you also have this corresponding term on the boundary of the free space, because so this Maxwell stress that you have essentially is just another way of rewriting the electric fields existing in the free space around you. And now the I think the important thing, which not a subtle thing that appears in the variation formulation. See, when we initially assumed this electric vector potential, we assumed one of the Maxwell's equation. One of the Maxwell's equation is the divergence of D equal to 0. There are 4 Maxwell's equations, two for electric field, 2 for magnetic field, for let's say a static problem. So one of the equations comes as divergence of D equal to 0. But as a consequence of this variational formulation that you develop, you get this corresponding equation for the electric field as an outcome of a variational problem. So you don't have to assume that a priori. And I think that's a very important thing. That even the not only the so you get balance of momentum, the first equation, balance of momentum as a consequence of a variation problem, but you also get this balance equation of electric field as a consequence of a variation problem. You don't have to assume that initially, and that is because you had a variation formulation based on A. And this electric field that I just showed here is outside the body. It has the same sort of structure. E is related to the D. But inside the body, it has again a nice structure that comes from the energy density function. E is derivative of omega with respect to d. So this, I think this is something that people might have seen if you have worked with elasticity, that stress is a derivative of energy with respect to deformation gradient. But this is something that comes out as a consequence of variational formulation in electroelasticity. The electric field is also a derivative of energy with respect to electric displacement. Right. So these are the kind of things that you see as a consequence of variational formulation. Now,
I have a question, Dr. Prashant.
yeah, sure.
Can you please elaborate more on the fourth criteria of the boundary condition? First Euler-Kirchhoff stress times N naught equal to 0. The fourth, top,
Okay.
from the top.
Yeah, this one here, right? Thanks. So that's nice. So good. Thanks for asking this question. So we have this body inside the free space, and essentially when we wrote down this energy, that this third term in the energy, what we are saying is we are specifying this electric field, and I think we are specifying the tangential component of this electric field by writing this energy here, because we have this E cross A. So this is the cross product E cross A dot with N. So this is the cross product over here. And the Maxwell stress. So this fourth criteria that you talked about is at this boundary we have that P times N naught equal to 0. And this P here is the Maxwell stress that comes from here, because that is in B0 prime. And this Maxwell stress is composed of these electric field and electric displacement. So essentially what we are doing here is we have some electric field in the free space, and we are just rewriting that electric field in the form of a force vector, which is essentially the stress tensor that you see here. So this Pn not equal to 0 that you get out of this variation formulation is equivalent to the original boundary condition that you had specified. The tangential component of E is specified. So
Okay.
this is not giving you something new as such. This is essentially giving you the boundary condition that you had in the form that you would want to use in doing your computations.
And you have a kind of that in the following boundary conditions, you have kind of that double brackets on the electric field. Does that mean there is a discontinuity? I mean,
Okay, thanks. Okay,
last
so here,
two.
yeah. So we've sorry about that. So we've got this double bracket over here, right?
Exactly.
Is this,
exactly.
yeah. So these double bracket correspond to the jump in P. So thanks. I should have said that. So this double bracket P is actually meaning that P outside minus P inside. So these are you can see conditions on the boundary del V0. So normally in a purely elastic problem, you would have the boundary condition that P times N naught equal the traction, right? Because P is the Euler stress is only inside the body. But here you need a jump in P because you have stresses inside the body and also stresses outside the body. So stresses inside the body are the Euler-Kirchhoff stresses, but stresses outside the body are this Maxwell stresses. So that's why we need these jump conditions. Does that answer the question?
Yeah, pretty much. Yeah, thanks.
Okay, thank you. Right. So what I was saying was you have this variation formulation based on A, but you can also write the variation formulation based on, so here A is actually related to the electric displacement, but you can also write a variation formulation in terms of the electric field or even the electric polarization. So you have another variable called polarization in the body, which is over here actually. So you can rewrite a variation formulation in these forms, and each of these will give you their own set of equations, which are in many ways equivalent, but in some ways they are not fully equivalent. And the second, okay, no, there's nothing more I want to say here. I'll see it on the next slide. So I think the first point we had already discussed. There was some Maxwell stress tensor is something that comes out naturally as a consequence of a variational formulation. And the Maxwell's equation, you had to specify one Maxwell equation to get the other Maxwell equation. But this was just the first variation, and I'm not writing down the higher variations because those equations become too long. But you feel free to. We've just published a couple of papers on this topic where you can see a very lengthy discussion on this. But a very nice thing that happens. There's another subtle thing that happens here, which we found out, which is not really discussed in. I couldn't find a place where this is discussed actually. And this thing was that if we had this condition that we have a body and there is a, let's say, a free space surrounding the body with a boundary, right? But if you take this free space to go to infinity, in that case, the formulation that you get from restricted free space and the formulation that you get from taking the free space to infinity are not equivalent. And they're not equivalent because in this case, what you see is the Maxwell stress that you have, that sort of that becomes non-unique. And just bear in mind that Maxwell stress is kind of an artificial construct just to rewrite the electric fields in the free space in a way that is amenable to computations. It is not a physical quantity, so to speak. It is what we use for computations. What physically exists in free space is just the pure electric field and magnetic field and their energies. But if you take so this is something we have a lot of discussion on this in the second paper. So I won't dwell too much on this, but it's an interesting thing to just to know about. Okay, so this was like a bit about variational formulations, and just to know that there's not a single variational formulation for the problem that you have had. You need to modify the variational formulation and move forward. So for example, if you remember, I discussed about these dielectric elastomers, right, where you have the sandwich structure and you have electrodes on top and bottom. So in this case, the body of the boundary of the body sort of corresponds with the boundary of V naught over here, because you can imagine that if you have a capacitor where you apply potential difference, that's a bad battery, but if you apply a potential difference, that's some V, then there is no all the electric field that's going to be there is going to be inside here, right? There is no electric field that is going to leak outside. Only maybe a little bit at the boundaries, but essentially there's no electric field outside the capacitor. So here this is a special case where B0 and V0 sort of are the same. So you need to modify a variational formulation a little bit to tackle such situations. So it's a very rich field actually to find out the appropriate variational formulation for the problem that you have, and you can do a lot of things here. We have not discussed anything about dynamic problem. We have only discussed about the static problem. So dynamic problem brings its own challenges. Okay, so I'm going to switch the gears a little bit. So from a more mathematical thing, let's go to a little bit more physical and computational thing. So let's now talk about instabilities in electroelastic and magnetoelastic solids, and how do we model them. So here is a couple of examples of instabilities that people have observed in experiments. So on the left is a paper from on magnetoelastomer. On the right is a paper on electroelastomer, and there are many papers. I'm just discussing results in these two. So what you see here is on the left, let's say, first is it's a grid of various situations, but if you go from left to right, you have a high magnetic field. Increase the magnetic field. If you go from bottom to top, you have you increase the compression. So the system that you have is you have a big block of elastomer, and on top of that elastomer, you apply a very thin layer of this magnetic material, magnetoelastomer. And then you try to compress this system. And on top of the compression, you also apply a magnetic field through it. So that is the problem that they have here. And you can see, so this leftmost figure is the one where there is zero magnetic field and almost zero compression. So the top surface is pretty much flat. And if you go from, let's say, from left to right here, you see that the top surface tends to wrinkle. So top surface tends to have this pattern here. You get this wrinkling in the top surface. And if you apply this magnetic field in while applying a pre-stretch or pre-compression, you see that that the wrinkling starts to appear quite earlier on. So you can see even higher wrinkles in this area. Here you can see maybe onset of wrinkling. Maybe it's not so clear. And here you can see the wrinkles are quite clear to see. So these are the pre-stretch as well as the magnetic field tends to enhance the wrinkling in the material. And if you have maybe just looked at this purely mechanical problem, it's a very famous problem which was first studied by Bio, I think 1965 or maybe before that, theoretically, that if you have this kind of a system and if you compress it, you will see these wrinkles. So that's kind of that's there. On the right hand side is something from an electroelastic solid. So what you have here is an electroelastic solid in the form of a tiny hemisphere, and you inflate it with gas, hydrostatic pressure, and at the same time, so it's a thin layer of it's not a solid hemisphere. It's a very thin layer of hemispherical shell or a hemispherical membrane, and across that thin layer you apply this electric potential difference. So remember, we had this system where you had this potential difference, right? So you take this capacitor, this thin capacitor, and you make a hemispherical shell out of the capacitor. So we apply hydrostatic pressure inside, but we also apply this potential difference. And then there are various things that happen here. One is that there's an extraordinary high change in the volume that is quite often seen in things like balloons, for example. If you have a birthday party balloon, you can see the amount of change in the volume is enormous, starting from this small to this big, right? So this is somewhat like this. But on top of that, you see, if you see this bottom left figure, then you can see that there comes a point where the hemisphere no longer remains a hemisphere. It sort of changes. There's a kind of a shape, that there's a dome that appears on top of hemisphere, right? Similarly, if you see here on the bottom right figure, I don't know if it's properly visible, but you see a lot of these wrinkles that appear along the hemisphere. And then the top right over here, if you apply very large electric field, if you apply very large potential difference across the thickness, then the capacitor will collapse onto each other. There will be short circuit and there will be dielectric breakdown. So there are a lot of things that can happen in a system like this. So modeling them is very interesting and challenging, and we have, let's say, done a few of these things, not all of them, but I'll just show you a couple of examples of how we model these some of these features. So I'll just talk quickly about instabilities in thin structures, thin electroelastic or magnetoelastic structures. And the key things that we are going to model is the limit point instability, which is the sudden change in the volume that happens, wrinkling instability, and the loss of symmetry. So loss of symmetry corresponds to something like this that we had at the bottom left here. Right? Wrinkling is what we see over here. And limit point is something that we see over here, where there's sudden change in the volume. So, the variational principles that I described earlier are not immediately applicable. We need to modify them. And the modifications that we require are, because we are going to deal with thin structures, we don't need a complete 3D description. We need 2D description. So we need a shell or a membrane kind of kinematics, because the third dimension across the thickness is something that you can assume what the deformation is going to be. But the in plane 2 dimensions are quite important. And then there's a special thing to model wrinkling, which is a tension field theory, which I discuss a little bit more about. And then we need to use these path following computational methods to actually recover to do the complete computation. And I'll discuss that a little bit as well. So let's just take a couple of sample problems.
Prashant, sorry,
Yeah.
I had a question. If it's okay,
Sure.
probably you might be addressing it later on. But when you have such large deformations, right, are you still using mesh method, or are you looking at meshless methods, or how do you do these computations?
So we do use meshes. Okay. There are a couple of things here. One is that the examples that I'm going to show you today, these are all done on symmetric structures.
Okay.
So your PDE becomes an ODE, and then you don't have to worry about those things. But there's some work that we have recently published, which I'm not presenting today, where we use isogeometric analysis, and then you can use meshes there.
But then still you would have I mean, if you have really large deformations, then you would still have a lot of mesh distortions, right? So how do you account for it?
You get mesh distortions, and then you can use some ALE formulations to deal with that, especially because you have to also worry about the free space.
Right, right.
But I think yeah, I mean, a little bit of remeshing may be needed, but I think that is something uh, I, that is something we can discuss. I'm not yet.
Sure, yeah. We can come back to it later.
Yeah.
Certainly.
Okay. So I'll just discuss a couple of these simple geometries to sort of focus on the physics part of it, and not worry too much about the computational part of it. So you have these hollow torus. So think of them like donuts, sambar vada, but they're hollow, and you can apply hydrostatic pressure. And on the left, I've got a case where you can sort of place a wire through the center of the torus, and then you can apply a magnetic field. So that gives you a magnetic field in this direction. On the right, I've got an example where you can apply an electric potential in the top and bottom of across the thickness of the torus, not the top and bottom, but across the thickness. And because it's a thin membrane, we just need to model the middle surface, and we'll exploit the symmetry that allows to convert PDEs to ODEs. So yeah, so essentially what we'll do is we've got these two parameters, as you can see, phi and theta. So you can define displacement functions, rho, which is a function of theta and phi, and eta, which is a function of theta and phi, with sort of so simple functions that sort of describe the entire displacement of the torus. And how do we do that is maybe that will be too much detail, but you can I can discuss if that is something you want to. So I'll just quickly show you the computational results. So what we are doing is we are just essentially varying the pressure, and we are varying these two things, electric and magnetic field. And here is one example of a, let's say, a couple of example of results that I've taken from these papers from our group. So on the left, you have, yeah.
Can I ask one question?
Yes, sure.
In previous slide, so you have you told that that a magnetic line you have used for magnetic field.
Mm-hmm.
This so how you are getting that magnetic field through passing current or?
Yeah. So okay, I should have said that. So this is the current carrying loop that
Okay,
passes
okay.
through the center of the torus.
Okay. Okay, thank you.
And also, I mean, I must add, this is like a cooked up problem to understand the physics more clearly. It would be quite not so non-trivial to realize it experimentally. Okay, so these are a couple of, let's say, some results that we saw for these systems, and what we see here is on the vertical axis, I plot the pressure inside the hydrostatic pressure inside the torus, and on the horizontal axis we have some measure of the deformation. So here, because these papers were written in different years, we had different things, but here we have the stretch at a particular point, and here we have the total change in the volume. But both of them sort of correspond to the same thing, that you have some measure of the deformation in the torus, or some measure of the inflation in the torus. So the initial part is sort of understandable, that so this dotted line here, I hope you can see the dotted curve here. Dotted curve here corresponds to the purely mechanical situation, where okay, so first look at that. So when you increase the okay, and there's another thing here. Maybe I'll discuss that later. So if you think about this, it depends on how you are loading the torus. So if you have, let's say, if you have let me draw. If you have a balloon which you are studying the deformation, so you can measure the volume and pressure in the balloon, and you connect this through some gauge to a let's say to a reservoir. So there are two ways of doing this experiment. You can either use this pressure gauge, to control the pressure inside the volume inside the balloon, and keep on supplying the gas accordingly. Alternatively, you can control the amount of gas that goes inside the balloon and measure the pressure that happens there, right? So you can have either a, typically you have in mechanics, right? You can either have a displacement controlled experiment or have a force controlled experiment. So this corresponds to that. So let's say if you have a displacement controlled experiment, then as you increase the displacement, the pressure first increases and then it falls down. So this initial increase is quite steep here. So the left, here we have not done computations to a very large value of lambda, but on the right you can see for E equal to 0, which is a red curve, if you keep on increasing the volume for a very large value, the initial stiffness is very high, but then it falls down and then it starts to rise again, right? So that is what we call as this point here on the top. That is what we call as the limit point instability. So imagine if you were doing a pressure controlled experiment. So and you were just monitoring the pressure and you want to increase the pressure step by step. So if you reach this value of pressure, and you want to now reach the next value of pressure on top of that, you need to supply a very large amount of gas to reach that value of pressure, and that would probably lead to a sudden expansion of the system. So if I right, so you'll probably reach from here to this point and then move forward. So it leads to a very sudden expansion of the system, and that is in many ways, I guess, undesirable. Maybe some cases desirable as well. But that is what we call as the limit point instability. The other important thing that you can see here is in the case of magnetic field, let's say when you start applying magnetic field, so all these different colors here, you start to see a small limit point, and then the actual limit point that you would expect. So there's an early limit point in the case of magnetic field. There's no such thing in the case of electroelastic material. And also in the case of magnetoelasticity and the electroelasticity, they have opposite behaviors. So here, in the case of magnetoelasticity, a magnetic field tends to increase the pressure that you require for a certain value of deformation, whereas in the case of electroelasticity, you decrease the value of pressure you require for a certain case of for same value of deformation. And another thing that is important is that when you have very large magnetic field, this curve here, you don't really have a stable state. I mean, you start a little bit. So maybe if I just move these things, you start in this area with a slightly small thing, and then suddenly fall down, and then it keeps on going down, right? So there is no stable state as such, or there is a very very small stable region. So large magnetic fields are quite hard to handle. So then we can see another view of this limit point instability, just to understand it better. So what I'm drawing here, so what basically we have, remember we had a torus, and we were looking, we had a cross section, and what I'm plotting here is just this upper half of the cross section. So I'm just plotting this upper half of the cross section at various values of pressure. So this legend here corresponds, the color corresponds to the pressure that you have at a particular value of that profile of the torus. So blue color is small values of pressure, and as you can see, small values of pressure corresponds to the area which is very close to the reference configuration. And then from this point on to this point, I think you have a sudden jump. So the pressure, the colors at this point and colors at this point are the same, right? And then color keeps on moving towards red as you move forward. But in this area, the colors are in the lower region. So the pressure is smaller in this area. Pressure is really high in this area. So if you were doing a pressure controlled experiment, you would probably you have this much deformation, and then suddenly you will have this much deformation, and you'll have a very large, very fat torus. So that is a way of sort of visualizing limit point instability. Okay, so yeah.
What is the orders of the strains in these two cases, whether it is electroelastomers or magnetoelastomers?
Okay, that's so these are actually two scales. So you can see, for example, the strains here are almost 3 or 4. Sorry, I'm talking about stretches. Stretches are 3 or 4. So strain is lambda minus 1, so 2 or 3. Now, these are very large strains. These are very very flexible elastomers with very large strains.
Okay, is it order of 200% or is it that?
Yeah, order of 200, 300%. Yeah.
Okay, thank you.
And let me just go back a little bit. You can see, for example, in these kind of experiments here, that these kind of strains really occur in these balloons or in these thin membranes. If you inflate them, you really get very large strains. So okay, so after going through this, let's move on to the next kind of instability, which is wrinkling. So I'll have to write a little bit here as well. So let's say wrinkling is something that you see, if you see a structure like this, right? If you have membrane, sort of you see this kind of wavy kind of behavior. That is what we refer to as wrinkling. And wrinkles occur because of in-plane compressive stresses inside of membranes. And the reason, let's say, from a more modeling or a mathematical perspective, this comes down to the theory that you use. If you use a shell theory or plate theory compared to membrane theory. So in a membrane theory, we don't have bending stiffnesses inside the material, whereas in a plate or a shell theory, you will have a bending stiffness inside the material. So what it means is that if you compress in plane, then the plates and shells are able to resist that compression, but membranes aren't able to resist that compression because they don't have bending stiffnesses. So they'll just suddenly very very quickly wrinkle as soon as the in-plane stresses become zero. And if you are interested in this topic, I would highly recommend this very nice paper by David Steigman. It's a very old paper, but it's still a very classical paper. So the main idea to model wrinkling is as follows. I'll just show here. Let's say you have some sort of a sample, and when you and you do apply uniaxial tension to that sample, right? So, and it will sort of extend in one direction, but it will compress in the other direction. So this compression is sort of measured by a function that we call as the natural width function. So let's say that the overall, so initial length was 1 and final length is lambda. So lambda is the stretch in the vertical direction. So it compresses in the horizontal direction by W of lambda. That can be, if it's an isotropic material, then it's quite easy to say it is just square root of lambda, 1 over square root of lambda, but it's not always isotropic. So this is something, an important concept here, W of lambda, which is a natural width. And now you see, if on top of this natural width, if you compress this further, then you can expect wrinkles to appear, because then you will have in-plane compressive stresses, right? So that is the key idea of tension field theory. What it says is that it basically goes back to elasticity. In elasticity, when you deform a material, we store some energy inside the material, right? And that is because the material resists that deformation. But in the case of membranes only resist in-plane tension. They cannot resist in-plane compression, because so imagine like a piece of cloth. If you compress a piece of cloth in plane, it will not resist any compression. But if you let's apply tensile force on a piece of cloth, it will resist a lot of tension. So that is the key idea here. So what it says is, just whatever energy that you have, W of lambda 1, lambda 2, just reduce that to something called as a relaxed energy, based on whether that material is being stretched or not. If it is stretched, then it is fine. If it is not stretched in a particular direction, then there is no energy in that particular direction. And then this was the key idea that was there in these early papers, and people have sort of, this is one paper by Greeny, and this is our paper. We have tried to extend this to the case of electroelasticity by taking this, extending this function to include also electric field. So you feel free to have a look at this paper for more details. But the key idea is the same, that you have defined natural width, and anything below that is zero energy. So again, this is an example of a result. So again, what I'm plotting here is, remember we had a torus and we had a cross section, and I'm just plotting this upper half of the cross section. So this is one of the cross section under one of the cases of loading, and you can see that if you the black curve, which is not really visible in the macroscopic diagram, is a solution without energy relaxation. So that is a solution that you would get without accounting for wrinkling. But if you actually account for wrinkling, then you get this dashed curve. So this is the entire profile of the torus. Oops, sorry about that. This is the entire profile of the torus, which is what is this over here, but only in the inner region. So only in this region over here that we have plotted in detail here, you can see that the dashed curve separates from the black curve. So the effect of wrinkling is quite small, but still, if you want to model it, you need to carefully model it, and probably it's small in this particular case, and it will be much more pronounced in some other cases that you may study. So if I just go back to my original plot for electroelasticity that I showed you, we had this kind of pressure versus volume curve, and you can see after reaching a particular point, the solutions after this that you receive, they are probably not correct if you do not apply the tension field theory. If you want these solutions to be correct, that's why we have drawn them in dotted line here. Any solution after the wrinkling needs to be recomputed using the relaxed energy that we showed earlier. Otherwise, that solution is not going to be absolutely correct. Or there will be some variations there. Okay, so that was wrinkling. And then there's a third form of instability, which is the global bifurcation. So remember when I was showing that experimental figure, we had this dome that was being expanded, and we had this sudden kind of a top dome on top of the other dome. So that is the kind of bifurcation that leads to loss of symmetry. And there are two ways of analyzing that. This is the first way, which is the most commonly used method. Which what it says is that let's say you know what kind of bifurcation is going to happen. So you assume that type of perturbation, and so what you say is firstly that delta E equal to 0. So I'm going back to the variational formulation. The first variation gives you the equilibrium equation, and the second variation gives you the condition of stability. And if delta square E is greater than 0, you are stable. But if it becomes 0, then that is the point of this bifurcation. So that's what we do. We assume a type of bifurcation and we put second variation to be 0. And then we search for a non-trivial solution and we find out that solution. The other way is a little bit more complex for the more general case. And there where you actually don't know what is the kind of perturbation there is, but you can check for all possible perturbations by checking the second variation. So I'll just briefly explain both of them. So let's say the first case where you know what kind of perturbation there is. So again, this coming back to this torus example, we had this torus and this torus was expanding. And what we assume was, let's say the bifurcation is such that you have a sinusoidal perturbation of the solution across the torus. So we assume this kind of perturbation where phi is the angle, phi is this angle from in this direction. And there we see that if that is the case, then the global bifurcation happens quite early on. Even so, remember we had wrinkling somewhere over here, but global bifurcation actually happens very early on here. Similarly, in some cases it happens very far away. So that was wrinkling here, and then again it starts to come very early on. So we need to sort of be aware of when a particular solution happens. So now again any solution after that you have got needs to be recomputed again, because this solution is no longer correct. We got the solution on the basis of assuming that the principal equations are correct, but they are no longer correct because bifurcation has happened. So this also essentially also gives you a nice mechanism to play around if you think about it. So let's say you somehow increase the volume of your torus and you reach here, and then you can suddenly increase the electric field and drop down in this area where you're no longer a torus because you are outside the domain of bifurcation. You can keep on increasing the volume, and you can suddenly decrease the amount of electric potential, and you reach in this domain where you're again back to being a torus. Then you again remove the electric field and you go back to being an area where you're no longer a torus. So this gives you a way of flexibility. Let's say if you're developing a soft robotic mechanism, it allows you to move between various configurations just by switching off and on the electric field or on top of your pressure. So you've got multiple controls there. Okay, so that was one way of computing. I'm aware of the time I'm exceeding it, so I'm going to quickly finish it. One way when you know the perturbations, but what if you don't know the perturbations? So this is a more general way of looking at second variation, and this comes down to, let's say, a little bit more of complex mathematics. Again, calculus of variations. So if you're familiar with calculus of variations, maybe you have seen that. If you're not, then this is a very interesting thing that you can see in a textbook, which I think a lot of people don't see normally, because often we are concerned with just the first variation. So if you have a function, if you have a functional, the second variation of a functional can be rewritten in this form. So here, this angular brackets are something like inner products. And P and Q are some matrices which are given here, which we get by taking lots of derivatives of this functional f that we have inside. And the necessary condition for stability, which is basically delta square pi greater than 0, is that P is positive definite. And the sufficient condition is actually a little bit more complex, and there is a rigorous mathematical proof for the sufficient condition, which I'm not going to go into. But if you can show that there is a function u that if you can basically solve for this function u given this differential equation such that this u is never has a determinant 0, then the sufficient condition is satisfied, and then you are extremely sure that the solution is stable. So we have used this in the context of magnetoelasticity in these couple of papers, in the context of magnetoelastic membranes. So you can have a look there. But what normally we do most of the time is checking the necessary condition P. So if you want to link this to, let's say, conventional elasticity, then this P tensor is sort of somewhat similar to your CIJKL stiffness tensor. It is similar to that. And Q tensor is something that we don't often see in conventional elasticity. So you always want the CIJKL to be positive definite, right, for stability. But that is only the necessary condition. This is actually the sufficient condition. So here is an example. Again, remember we had this torus, and I'm just plotting here the top profile of this torus of the cross section, and the solid curves that you see here at small pressures and a given value of magnetic field. These are the stable curves where the solution is definitely stable. It satisfies both the necessary and sufficient conditions. The dotted curves at the very outside over here, these are definitely unstable, where the necessary condition does not hold. So it's definitely unstable. But these dashed curves in the intermediate regions here, these are where the necessary condition is satisfied, but the sufficient condition is not. So these are very important, because in a lot of methods of analysis, people only check the necessary condition and they would declare that this to be a stable configuration. But the sufficient condition is not quite satisfied. So we don't yet know whether they're definitely stable or not. You need to probably check them in a bit more detail. So just to see, I mean, yeah. So this is something of a tricky issue and needs to be dealt with carefully. And I think I'll probably skip the last slide here and I'll go straight to the conclusions. But I think I've exceeded time quite a bit. So just to summarize, we saw modeling framework for large nonlinear deformation in soft solids, and I described hopefully variational principles for electroelasticity, not so much for magnetoelasticity, but it was quite similar. It goes in a similar vein, and we saw some different types of reversible instabilities and some mechanisms to model them. Especially we looked at limit point wrinkling and global bifurcation. But of course, I mean, there are lots of open questions in this area. First of all, we have not yet done anything in the dynamic regime. So what if you have very fast dynamics? Then the variational principles need to be rewritten. You need to go back to basic sense, look at the principle of least action. There might be some effects coming from viscoelasticity, which bring in friction. Then again, going back to your original question, Ajay, I've only shown simple cases where I had converted PDEs to ODEs, but if you want to really solve PDEs, we're actually using IGA to describe the surface geometry nicely, and it can provide a general solution for wrinkling. I can expand on that later on if there's more interest. And then the most important thing is, how do we actually, once we understand these basic concepts clearly, how these instabilities occur, how do they interact with each other, how do we use them to exploit them in engineering design? So that's me. And we have an open position to tackle these challenges, by the way. So feel free to email me if you want to discuss that. Thanks a lot so much for being patient. That's me.
Thank you very much, Prashant. Really interesting talk. I think we can open up the forum for audience if they have any questions. I certainly have a few questions, but I think I'll hold off on that. Are there any questions? Okay. So I mean, probably I asked this because like I'm more of a computational guy. So probably, I mean, like they say, everything is for me, everything is like a nail and a hammer problem, right? So it goes back to the computation thing, right? I mean, like, so when you're setting up a wrinkling problem, right? I mean, essentially, it's like a buckling problem. It's
Yeah.
an instability, right? So it's basically you have multiple solutions, and you can. If I think of simple like a column and you apply a load, a compressive load, it's going to buckle. It
Yeah,
means
yeah,
go on the left side or on the right side technically. So there's both of them are equivalent solutions, right?
yeah, yeah.
So I mean, I think wrinkling would pretty much be a similar problem in there.
Yeah, so I think so let's go back there. I think
How
that's
do we, yeah.
so here essentially there are two ways to tackle wrinkling in thin structures. Now, if you have this is one of the ways to do it in the case of membranes, and the good thing in membranes is that membranes don't have an out of plane. Let's say membranes don't have bending stiffness. So I mean that is the main thing here. That because they don't have bending stiffness, what this like basically in this brilliant paper and in this and associated literature, what people do is they it's let's say they look at it from a more mathematical perspective, and they say if there is no bending stiffness, then basically you would not see wrinkles like these that I've drawn here, because these correspond to bending stiffnesses. So what they say is you will have wrinkles in the case of membranes. You will have wrinkles with infinitely many wrinkles that you see here that you can't see here. You can see here finite number of wavelengths, but in the case of membranes you would see infinitely many wavelengths, and they will be very close to each other. So the tension field theory, what it does is it only tells you when the instability happens and the direction in which it happens and the region in which it happens. It does not give you let's say the exact profile of this wrinkles that you have.
Okay,
So,
I see.
so here, for example, we can only find out the region that okay, in this region wrinkling happens, and it will keep on happening, and this region can expand or contract depending on when you increase the load.
I see. Okay. So it's more like getting a region rather than the actual profile of the deformation.
Yeah, and now so to follow up on that, now if you want to actually find out this kind of profile that we have here, then you need to move from membrane to a shell theory. And if you have a shell theory, shells will have shells or maybe plates for a flat structure. Shells and plates will have bending stiffnesses, and with that, again, you apply the criteria. The basic process is that first of all you find out the point at which bifurcation starts to appear, and at that point onwards, you will sort of find the direction in which bifurcation happens, and then you will do the post buckling or post bifurcation analysis to find out how these profiles start to appear.
Right. So that was my question. So when you said post bifurcation analysis, bifurcation occurs, but then both the solutions are equally feasible, right? So you're basically will have to kind of push the solution in one direction somehow, or
yeah. So in some sense, yes. So I can sort of say from a more mathematical perspective. So I was discussing this energy functional, right?
right?
So basically, in simple equilibrium, delta E is 0,
Right.
and delta square E would be positive.
Right.
But now, when bifurcation happens, delta square E becomes 0.
Right.
So now, and this basically will say, okay, or maybe U3. And then now you will be looking at now delta cubed E with these U2 and U3.
Okay, I see.
And then you would see, okay, which one of them is sort of minimizing the total energy.
I see. Okay, I see. Okay.
And I think that's the main idea behind this bifurcation analysis.
So, but then did you also try to look at like tensile loading? Because I think you looked at the compressive loading, right? But then even during, if you apply a tensile loading on a thin membrane, that should also lead to wrinkling.
Yeah, so this here, for example, this very much is sort of tensile loading. So imagine,
Okay.
so this was from this inflation of a torus. So imagine you have a balloon.
Okay.
You are inflating the balloon, and you can actually see this yourself. If you have a party balloon, and you inflate the party balloon, I can draw it here. If you inflate the party balloon and you can tie it up the knot here,
Right.
in this region, you can actually visually see wrinkles.
Right. Absolutely. Yes.
Yeah, because this is a region where you tend to get compressive stresses. In one, so compressive stresses are only in one direction. The other direction is still tensile.
Yeah.
So that's why you see wrinkles in one direction.
Yeah, because this also like kind of comes back to like a biomechanical problem. I think you're showing something about the skin modeling, if I remember right. So that's again kind of where these kind of wrinkling would come in tensile loading conditions.
Yeah. So for example, if you have a skin patch somewhere on your face and you are smiling, so we normally get facial. So you can get wrinkles on your face because of two reasons. Either you get old or you are smiling. If you're smiling, you get expression wrinkles. Right. So even those kind of, if you have skin patches and you have expression wrinkles, then you sort of need to model them and have appropriate materials that can replicate the same phenomena. Otherwise, imagine the underlying layer is wrinkled, the outer layer is still flat, so you will have debonding.
Right.
And therefore it will sort of fall away. So you need to have the same stiffnesses, same mechanical behavior.
Right. If there are any questions from the audience, I think please feel free to unmute yourself and ask a question. And
yeah.
So maybe again they don't seem to have anything at the moment. So let's give them a little more minutes to maybe ask something. Coming back to the IGA, the isogeometric analysis, right?
Yeah.
So why not meshless techniques? Why IGA? I mean, because again, even though IGA is pretty popular, again, even though you come back to having a mesh, right? I mean, again, once you have a mesh, it always comes back to the same distortion problem. I mean, 200, 300%, 600% is still manageable. Like Ogden model could handle 600%. We used to do that with the rubber materials. But then,
I think one of the reasons for IGA was, let's say, more closer interaction with the engineering design. So if you
basically have the same nerves and B-splines that you can use, and
exactly, so you can take the CAD geometry and just put it in your model, which is, I'm not sure if it is possible with meshless method. I'm not familiar with them very much, but probably it is. But with IGA, I think that is one of the major advantages when everyone sort of is attracted to it. Is you can there's no geometric error, so to speak.
Right. So you don't have a mesh and you don't have this discretization error coming in to some extent.
Yeah.
Okay.
I had a quick question. I think I posted it in the Q&A section, but it didn't come through. I had a quick question regarding the fatigue failure. For example, right now we are practically trying to use these instabilities and wrinkles to sort of move and change shape and deform the configuration to and forth, for example, and we are right in the instabilities region. So wouldn't it cause some fatigue problems for the material? For example, we're trying to use it like in the applications like soft robotics where constant movement is required. Wouldn't it affect that?
I'm sure it will definitely be the case. So I think the things that I have presented are, let's say, relatively very simple, where we have no friction, we have no damage, we have no plasticity and so on. But I think you're absolutely right. So when you have these constant motion, even let's say not constant motion, even for static motion, when you have very large deformations with elastomers, we tend to get some damage that starts to build up over time. And with constant motion, fatigue definitely builds up. So those kind of phenomena needs to be accounted for when we look at soft robotics. So,
Yes, exactly. Because as far as I know, it's like in elastomers and rubber materials, there is usually the hysteresis problems, and the material itself heats up, and there's some sort of heat dissipation, and we again are giving some magnetic fields and electric fields. So it all sort of builds up, and that was a quite an interesting talk. Thank you very much.
Yeah, thank you for this comment. I think you're absolutely right. So we have skipped a lot of things related to viscoelasticity, which gives you that hysteresis or damage because of fatigue and large deformation. So that is definitely something that needs to be done. Yeah.
Yeah, I have a question.
Hi, Professor. So it's a quick question from my side. So can I ask?
Yeah, absolutely.
Yeah. So what about these demagnetizing field effect? Say material itself is magnetic material, so it will affect the outside magnetic field when we are considering the material means magnetic material inside. So how we can consider these demagnetizing field effect within the modeling?
I think that if you sort of go back to the original this slide here, if you look at you basically need to construct the variational formulation appropriately for that. So here, there's too much noise on the slide now, but when you have a system like this, can you maybe mute your mic? Sorry, I cannot hear this. So when you have a system like this, this accounts for any change in the electric field or magnetic field because of the material. So I think if I understand your question correctly, what you're asking is, I'm applying a magnetic field from outside, but because of the presence of the material which magnetizes, there is change in the magnetic field in the surrounding region. So this is taken care of by the variational principle. And if you solve these equations completely, that will be implicitly taken into account.
Yes, this is what I am asking. Thanks a lot.
Yeah.
And can I ask about the solution of these PDs? So are you using shooting method, or are you treating these equations as boundary value problem?
Okay, so there's a combination of a lot of things that we do. So one thing is that the solutions that I showed you were not completely of these PDEs. We don't solve these PDEs completely right now. Right now, what we have done is we have done the mathematical analysis to derive them completely. So this was done only just now in let's say last couple of years. What we do is we simplify these PDEs for the context of problems that we solve. So if I just go back to this problem, let's say, in this problem, what we had done is because it's a thin, so let's look at this electric case. So because it's a thin kind of structure, and we know that the electric field is, let's say, applied by potential difference on top and bottom, and there's nothing outside, we can simplify this problem considerably. We can also, because it's a thin structure, we can also sort of assume that the electric field is going to be just perpendicular to the thickness direction, and that simplifies the problem considerably. And then that coupled with assumption of the symmetry of the problem, we can actually convert this PDE to ODE. So that's what I had written here, convert this PDE to ODE. And then this ODE can be solved by various methods. So if we get a boundary value problem with an ODE, and shooting method is a very nice technique to solve it. If you have, in this case, it's a non-linear kind of a system, but if you have a linear system, then there are other methods like compound matrix method, which can solve ODEs quite nicely. But if you want to solve the PDEs completely, then that is the work that we are currently doing. Some people have done it up to certain degrees, and people use a combination of finite element analysis and with various things. But the main challenge that comes is in solving those PDEs with this large deformation is that you also need to account for the free space. And when you have this large motion of let's say when you inflate the balloon displaces quite a lot, and because of this large displacement, the mesh in the free space distorts considerably. So you have to use some techniques to take care of that.
Hello.
Yeah.
I have a question.
So
Yeah.
one more question.
Yeah.
Yeah. So you have talked about necessity condition and sufficient conditions. So can you please throw a light on how we can utilize, means how we can came to know about these sufficient conditions and how we can utilize it for finding out the stability, instability in the systems?
So I think
Little bit
okay,
details.
yeah. So yeah. So this is basically very much equivalent to what I said for like when I said that for a function you need f prime of x equal to 0 and f double prime to be greater than 0 and so on, right? For a simple case of calculus. So this is equivalent of that for variational calculus. And essentially what we do is we write the integral of the second variation in a form that we in this particular form where we have two matrices P and Q, and you can if you know this function f, you can actually write down these matrices P and Q just by taking derivatives. And what we mean is that I mean given a certain configuration, you want to find out whether that configuration is stable or not. So you substitute those configurations in this P and Q and check these conditions. So these conditions are just there to be checked. I mean, there's nothing to derive here. You just need to rewrite these conditions corresponding to your problem. So this is written with respect to one particular problem. I'm not sure what else can I say. I mean, does that probably answer a question?
Yes, sir.
Okay,
Thanks a lot.
Thanks. So another question from Manu: can viscoelasticity delay the onset of instabilities, or can viscous effects cancel the wrinkling in course of time? Well, the answer to that is to both of them is yes, but I think so from a physical perspective, that sort of seems to be the right thing, that if you have a viscoelastic system, then any sort of surface perturbation that you have might actually die down. But the thing is that with viscoelasticity, this problem becomes completely different, and that happens for a couple of reasons. One is that for viscoelasticity, the energy is not conserved. That is the main thing there. And because your energy is not conserved, you cannot really talk about minimization of an energy. Because it's a minimization of energy is applied to conservative systems. Viscoelastic systems are non-conservative systems. So this analysis that we described for variational calculus is no longer applicable. So what we do in these dynamic systems is so the definition of instability itself changes in many ways, and you need to move from this definition of instability and let's say talk about configuration of the system, and the configuration which is flat and configuration which is with wavy nature. So you need to talk about those configurations, and you need to look at stability in a more dynamic sense. So for example, There's a lot of work that is done in the case of stability of dynamical systems, and one way of looking at this instability is the system is, let's say, oscillating or moving, and it keeps on oscillating or moving with small amplitude in a small region. So that is called as dynamically stable system. If you slightly perturb it and it sort of goes away, then it's a dynamically unstable system. So I think viscoelasticity is very nice for looking at solving problems and actually looking at materials, but when it comes to stability, it's completely different animal. So it's a very interesting area to go into, but you need to sort of redefine things from the start. That's a very good question.
Are there any other questions? If not, maybe we can close the session.
Thanks a lot, everyone, for the interesting discussion.
Thank you everybody for joining in, and thank you Prashant for taking time and joining us. It was really informative, and I learned a lot about the variation forms and instabilities, and I hope all the students who joined in and all the audience who joined in also enjoyed the lecture. I hope everybody has a nice weekend, and see you in the next lecture then. Thank you very much, and have a nice day. Bye.
Yeah, have a nice weekend, everyone. Thank you. Bye-bye.